In this video, I explain bias, variance, irreducible error more clearly using a regression error example. Okay, let's see. Let's consider a ground truth model y equal to fx plus epsilon. Here epsilon is irreducible error. From some running model, we obtain f hat x from training data. Okay, so let's say there is some training data point x1, y1, x2, y2, up to xn, yn. So from the training data, we learn some model and achieved f hat x. The expected error of fx plus epsilon minus f hat x squared. This is mean squared error of regression problem will be the test error. So here the expectation is with respect to x, new sample observation, test data point, which comes from some data generation process. And also this expectation indeed with respect to f hat. So here f hat is also a random value or random function which trained from a training data point set from x1, y1 to xn, yn. Essentially, they generated from some data generation process. And f hat trained from the random data set. So f hat is a random function indeed. So here the expectation is with respect to not only the test data point x, but also the training data point. Right. So let's rewrite the mean squared error, which is fx minus f hat x plus epsilon square, which is equal to expectation with respect to x, expectation with respect to f hat, or we can say with respect to training data, fx minus f hat x square plus sigma square. Here the sigma square is the variance of epsilon, which is irreducible error. And this part is reducible error. Okay. And we can also decompose the reducible error into two different parts, bias error and variance error. Okay, so how can we decompose? So this is expectation with respect to x, fx minus expectation of f hat x square plus expectation of f hat x, so here with respect to d, minus expectation of hat x square. Plus irreducible error. Right? we can do that because fx is a constant with respect to the training data point. Even if you control the training data point, fx value never change. So here fx is just constant. So fx and f at x are independent. So from the independency and the mean or expectation of f at x minus expectation of f at x is equal to 0, we can decompose this, right? So in the end, we have this. Minus expectation f hat x square plus f hat x minus expectation of d f hat x square plus sigma square. So this is irreducible error. This is bias error. And this is variance error. Why? So here, this value is variance of f at x. This value is error comes from the limitation of your model. If your model has a lot of degree of freedom, a huge flexibility, then your expectation with respect to the data set of f at x can fit the original function fx. On the other hand, if your model is very small degree of freedom, very non-flexible, your model cannot fit fx even if you have an infinite number of training data points. So on the other hand, this part is variance. If you have a huge number of degree of freedom, then your model is too sensitive to your training data point. So when you control very tiny amount of training data point, you can change the f hat a lot. So maybe you can observe a huge variance almost all x range, right? And because the sigma square is irreducible error, we cannot control this. So in your model design and your machine learning process, you have to consider bias and variance. And you have to control the model very carefully so that the balance between bias and variance is nice, so that the sum of bias and variance is minimized.